So welcome everybody. Today our speaker is Arman Taghavi-Chabert from Politechnika Łódzka. So Arman was for the long time also at our institute in Warsaw. And before he has held many positions, but he finished his PhD studies in Oxford under Lionel Mason. So Arman, you can start. Thank you.
Okay, so thank you very much for the invitation, Wojciech. Some of you might be already familiar with this talk, which I gave at various places. So actually, the subject of my talk is very much connected to the work that was carried out in Warsaw in I guess in the 1990s. The motivation is to investigate the interaction between conformal geometry and Cauchy-Riemann geometry. And there are at least two points of contact between these two geometries. So the first one is comes from pure mathematics and is due to Charles Fefferman, who in 1976 constructed in a canonical way a Lorentzian conformal structure on a circle bundle, canonical circle bundle of a CR manifold. So I will explain what this means in a moment. So this was, as I said, it was very canonical and was motivated in part by Fefferman's investigation of the Monge-Ampère equations. On the other hand, we had, so there are many contributors to this topic. So starting from the golden age of general relativity, so we had the mathematical physicists such as Robinson, Trautman, Penrose, Kerr, Newman, just to name a few. They were investigating exact solutions to the Einstein field equations in dimension 4. And these, so the complex numbers kind of unexpectedly arose. So the presence of complex numbers motivated Penrose to formulate his twistor theory, whose initial aim was to unify quantum mechanics and gravity. But there was another aspect of this complex geometry or complex analysis lurking in these solutions. And it took many years, maybe until maybe 1976, I think, it was realized that what we're dealing with is CR geometry. So how does it work? So these exact solutions to the Einstein field equations are equipped with a so-called congruence of null geodesics that is shear-free or non-shearing, as I call them. And the leaf space of these congruences, these foliations by null curves, turns out to be a CR manifold. And there was a program started by Andrzej Trautman at the University of Warsaw, and three of his former students, or students at the time, Jacek Tafel, Jurek Lewandowski, and Paweł Nurowski, worked on this connection between the exact solutions to Einstein equations and CR geometry. So there were a few landmark papers. So there was one in 1990 where Lewandowski and Nurowski described, gave a very, very nice description of these Einstein Lorentzian four-manifolds. And shortly after, or around the same time, so Lewandowski, Nurowski, Tafel, also wrote an article that makes a connection between the Einstein field equations and the realizability of the CR structure. So I'll be making this more precise. Roughly speaking, the idea is that the CR manifold is a prototypical example of a CR manifold is a hypersurface in complex space. But not all CR manifolds are hypersurfaces, and we say that that they are realizable if they are hypersurfaces, or they are diffeomorphic CR equivalent to hypersurfaces. So this was a result of the 1990s, and also revisited later by Denny Hill, Lewandowski, Nurowski in 2008. Okay, so the aim of my talk is to understand the work of Tafel, Lewandowski, Nurowski, and Hill in terms of the Fefferman construction. So, so Fefferman's contribution is a construction, whereas the contribution of the Warsaw School is more of a description. And I wanted to fill in the gaps in that respect. And actually, I got a little, by doing so, I got a little bit more than what I expected. And I managed to re-express the CR realizability in terms of what I call BGG type equations. So they are CR invariant differential equations that are used in parabolic Cartan geometry. Okay, so I will give a very basic introduction to CR geometry. So, as I said, the CR manifold is a real hypersurface in complex space. So some examples, very simple examples, include, so a real slice, the hyperplane, the real hyperplane in CM plus 1. So this is the first example here. Can also, another nice model is the odd dimensional sphere, which is given by this equation. So here the alphas and the betas run from 1 to m, and the H alpha beta bar can be thought of as a Hermitian form. Actually, it is a Hermitian form. Here it can be regarded as a Kronecker delta. So this would be the equation of an odd dimensional sphere. Another equation, another example of a CR structure is the so-called hyperquadric, which is given in this form. So the first one is said to be Levy flat. It's not so interesting. It's really diffeomorphic to R cross CM. And the other two are CR diffeomorphic or CR equivalent to each other locally. Okay, so we have, if we're given two real hypersurfaces in C2, one can ask the question, are they biholomorphically equivalent? In other words, can we find a Riemann mapping theorem for C2? So this question was asked by Poincaré in 1907, and he actually gave the answer to this question. So the answer is no. So if you take, for instance, the ball in C2, then one can show that it is not biholomorphically equivalent to the polydisc. So the claim that it was proven by Poincaré already. So then the question is, can we find differential invariants to distinguish these biholomorphism classes of hypersurfaces? Okay, so I will come back to this in a moment. Before, I want to give a more abstract definition of a CR manifold. So by abstract, I mean we do not view CR manifolds as embedded in Cm+1. So an abstract CR manifold will be a not-dimensional smooth manifold. So let's say 2m+1, which is equipped with an almost CR structure. So this is a complex rank M distribution, which intersects which does not intersect, well, which intersects its complex conjugate trivially. So this is a normal CR structure. And if this rank M distribution is involutive, so that is closed on the Lie bracket, then we called our manifold CR manifold. And the almost CR structure is a CR structure. So there is an equivalent way of expressing this complex rank M distribution in a sense that this is really the eigenbundle of a almost complex structure on a distribution which I call H, which is of rank 2m. So you think of H as a hyperplane distribution on your odd dimensional manifold, and there is the rank of H is even dimensional, and then you equip this hyperplane distribution with a complex structure, a bundle complex structure. So in particular, a real hypersurface inherits this complex structure from the ambient complex space it is in. So so it should be the ambient Cm+1. It's not Cm+2. So there are a number of invariants that you can construct. Well, basic invariants that you can construct from these CR structures. The first one is the Levy form, which is a Hermitian form on this hyperplane distribution. So you just take two sections of H10 and you pair them as follows. So you take the conjugate of 1, so it would be the complex conjugate, maybe I should say, is denoted H01. Then if you take the Lie bracket of these two and project onto the quotient of the complexified tangent bundle by the complexified hyperplane distribution, then you have a Hermitian form that takes values in a line bundle, which is given as this quotient. So if we have a Hermitian form, then you can define its signature. So the signature of a Hermitian form is simply the signature of its symmetric part or real part. And if two CR structures have different Levy signatures, we can be sure that they cannot be CR equivalent. So this is a very simple example of an invariant. So for the rest of my talk, I will focus on the case where the Levy form is non-degenerate, so it has full rank. Okay. So let me carry on. And so this is so I've already mentioned some examples of basic CR manifolds. Here I'll go back to this CR sphere. So this is called the flat model in I guess in parabolic Cartan geometry. So here is how you would construct this non-degenerate CR geometry. So you choose a Hermitian inner product of Lorentzian signature on a complex vector space. Because it has Lorentzian signature, you can consider the cone of null complex lines in this complex space of dimension m+2. And then you take the complex projectivization of this null cone, and you end up with an odd dimensional sphere. which is a variety in complex projective space of dimension m+1. And one can show that this is actually equipped with a positive definite CR structure. So CR geometry for non-degenerate CR geometry is a curved analog of this sphere, of this construction. So projectivization of a cone of null complex lines. So I'm not going to go into details, but this was actually the strategy adopted by Cartan in order to solve the equivalence problem for CR geometry. So he did this in dimension 3 in 1932, and this was extended later well, actually 40 years later by Chern and Moser in dimensions greater than 3. And what these people found notably is the obstruction to CR flatness in terms of invariant, CR invariant tensors. So by CR flatness, I mean a CR manifold is CR flat if it is CR equivalent to this flat model that I just presented earlier. Okay, any question? Okay, so I will carry. So I will adopt a more down-to-earth approach to CR geometry. I will be using the so-called Webster calculus. So how does it work? So if I start with a CR manifold of dimension 2m+1, okay, so all my CR manifolds will be non-degenerate. So I have a hyperplane distribution. And if I choose an annihilator of this hyperplane distribution, this gives me a contact form. So it's a contact form because the non-degeneracy of the Levy form tells me that the hyperplane distribution is a contact distribution. So if I choose a contact form, then there exists a unique connection on this manifold that preserves the contact form and its Levy form. So the Levy form of the contact form is essentially the exterior derivative.
Excuse me, may I have a question? This contact form is just unique or just family of forms?
No. So here I'm making a choice. I'm making a choice of a contact form. Generally, there will be no distinguished contact form. So here I'm making a point. So here I want to draw an analogy between conformal geometry and CR geometry. So in conformal geometry, you have an equivalence class of metrics, and then you can choose a metric, and you have the Levi-Civita connection. So here I can play the same game. I have my CR manifold. I have a family of contact forms that are conformally related, and I'm choosing one. And so there is this theorem or proposition due to Webster that tells me that I have a unique connection which has some properties. So one of them, it preserves the contact form, and it also preserves its Levy form. So is it clearer?
Yes, thanks.
Yeah. And okay, besides, so it has also torsion. So it's not like the Levi-Civita connection. So it has torsion. But this torsion is prescribed, has prescribed symmetries. So if I can write this out in terms of an adapted coframe, so theta is my contact form, and then theta alpha are joined to theta and are actually the annihilator of the H01 distribution. So by adapted, I mean that d theta can be expressed as the Levy form in such a way. So I have a Hermitian matrix of functions that are given, that are the components of d theta with respect to this coframe. So of course, so I can never get rid of this H here, and H, this Levy form, is part of the torsion, and you can never get rid of it. On the other hand, if you take d theta alpha, then you get well, these structure equations. So gamma here would be the connection one form of this Webster connection, and this capital A here is the so-called Webster torsion, and it's symmetric in its indices. So I can raise and lower indices using this Levy form, but when I do so, I change the type. So so for instance, here I have A alpha upstairs, beta bar downstairs. If I lower the indices, so I get well, so yeah, so so this should be the complex conjugate, I guess. So then I have a change of index type. So of course, so this connection depends on the choice of contact form, and so if I change my contact form by a conformal factor, then I have an induced change of Webster connection, which is quite complicated. So I'm only giving you the formula in schematic form. So this is not really what it's, it's actually more complicated than it looks. And this torsion A also changes in a particular way. So this epsilon here is essentially the exterior derivative of this psi, which is in this conformal factor. So just as in conformal geometry, you can also define density bundles. So one simple example of a density bundle. So there'll be complex density bundles. So I have my distribution, complex distribution H01, which is of rank M. So the annihilator of H01 has rank M plus 1. And if I take the top power of the exterior algebra of this annihilator of H01, this gives me a complex line bundle. And if so then I can assume that I can take a particular root of this complex line bundle, and it defines, well, another complex line bundle, which I denote E minus 1, 0. And in this case, I will say that a section of this bundle has weight minus 1. So you can take the complex conjugate of this bundle, and you get a bundle which would be E0 minus 1. And I can take powers of these and tensor products, and I end up with plenty of complex line bundles that are parametrized by real numbers, W and W prime. And there is a condition on W, W prime. So if I take the difference, they should differ by an integer. So you should think, so if you're not really familiar with these density bundles, you should think of them as being sections of the annihilator of the, well, I would say the anti-holomorphic vector bundle. So there is, well, so the weight 1, 1 is rather special. So I don't want to go into too many details, but one can show that, so if I choose, let's say a density, nowhere vanishing density of weight 1, 0, which I call sigma here, I can pair it with its complex conjugate. So this gives me a density of weight 1, 1, which is real. And we can show that this is actually equivalent to a choice of contact form. So I'm skipping a lot of details here. I don't think I have time to go through all the details. And conversely, if you choose a contact form, then this contact form determines a density of weight 1, 0, but only up to phase. I mean, this is quite obvious because of this pairing. So if I change my theta by e to the power of I phi, then I still get the same theta. So this will play a role later in the context of the Fefferman construction. Okay, so just as in conformal geometry, you can construct CR invariant operators on the basis of this Webster calculus. I don't know how many of you are familiar with this calculus that is used by people in parabolic geometries. So I'll try to explain roughly what all these mean. So here is an example of an invariant differential operator. So it is applied to densities of weight 1W. So if I take two covariant derivatives of this density along the along the 1, 0 distribution, so the holomorphic distribution, and I adjoin to it a term involving this Webster torsion, then one can show that this is actually invariant. So if I change my contact form, I will get the same expression now in terms of the Webster connection associated to the new contact form. So this is an example. Another example is if I take a density of weight W0 and I take the covariant derivative with respect to vectors in the anti-holomorphic vectors, then this is invariant. Then there are some restrictions that we can make, some very special cases of these two operators. So the first one is if I restrict myself to densities of weight 1, 1, which are real, I get the same operator here. And I call this operator S. And another one is called the operator E. And it's a bit more complicated. So I'm taking, this time the operator is applied on densities of weight 1, 0. And it is sent to actually two operators. So the first one is this one here, and the second one is that one here. So what's the meaning of these operators? So we're interested in the kernel of these operators. So for the first one, so if I know that I have a density sigma that is annihilated along the H01 directions, then this tells me that I have a closed section of the canonical bundle. So the canonical bundle is the top form of the annihilator of 01, H01. The second operator, so if I have an element of the kernel of this operator here, then this S determines, so my density S of weight 1, 1 determines the contact form. And with respect to this contact form, the Webster torsion vanishes. And this tells me that the Reb vector field associated to the contact form is a transverse CR symmetry it's a transverse symmetry. So it's a symmetry of the CR structure. So if I take the Lie derivative of any vectors in H10 along the Reb vector field, then it's still an element of H10. Yeah, so typically I write on the board when we come to this stage, but yeah, so if you have any questions, just let me know. And the other operator, which I denote by E, so this so if I take, so elements of the kernel of this operator will give me a CR analog of the Einstein equations, which I call CR Einstein. So I will skip a lot of details here. So the idea is that there is a Schouten tensor or trace adjusted Ricci tensor associated to the Webster connection. And if this Webster-Schouten tensor, as I call it, is proportional to the Levy form, then this is called a pseudo-Einstein structure. And if in addition, the Webster torsion vanishes, then we call this a CR Einstein structure. So I will come back to these conditions in a moment. Okay, and then, so this was for the geometrical side of things, but the more analytical side of CR geometry is really concerned with realizability. So as I said, when is an abstract CR manifold realizable as a hypersurface in Cm+1? So for this, we need the notion of a CR function. So a CR function is essentially the odd dimensional analog of a holomorphic function. So we require that a CR function, at least locally, so it's a function that is complex valued and annihilated by all the vectors tangent to the distribution H01. So you think of X as being an anti-holomorphic vector field. And one criterion that can be used to characterize a CR, an embeddable CR manifold. So if it has dimension 2m+1, then the abstract CR manifold must admit m+1 independent CR functions. So think of the CR functions as providing a CR chart. So they are complex values. You want an embedding into Cm+1, so you need m+1 CR functions. So it makes complete sense. So there are a number. So realizability is not automatic. There are a number of results related to this. So Hans Levy in 1957 constructed an example of a non-solvable differential operator on the CR sphere in dimension 3. So this is, so he essentially took the Levy operator or the Cauchy-Riemann operator on the CR3 sphere. And he showed that for some specifically chosen functions on the 3 sphere, G, there is no solution to this differential equation. So there is no solution F. And using this result, one can show, so Nirenberg in 1974, and then Jakubowicz and Trev later, showed that actually there are non-realizable CR manifolds in dimension 3. And this question was also addressed in higher dimensions by people like Kuranishi, Akahori, and Webster much later. So in high dimensions, but a dimension strictly greater than 5 with positive definite Levy form. So they showed, and it's a pretty hardcore analysis, they showed that any CR manifold of dimension strictly greater than 5 with positive definite Levy form is embeddable. So as of today, it remains a conjecture whether this is still true in dimension 5. Okay, so so there are various. So I'm a bit short of time. I should look at the time more carefully. So there are various other criteria for CR realizability that were proved by notably Jacobowicz. So I'll give you two here. So the first one, so the Jacobowicz proposition. So a CR manifold is locally embeddable if and only if it admits a transverse complex valued vector field, L, that preserves the CR structure. So this is the condition. This is what I mentioned earlier on, actually, but I mentioned this in the context of a real vector field. So if L was a real valued vector field, then this would be a CR symmetry. So this is a complex valued vector field. So it's a weaker condition. And another criterion is given by Jacobowicz theorem. So the CR manifold is embeddable if and only if it admits M strongly independent CR functions. So it's not enough. So M, if you have only M of them, it's not enough to have embeddability. Or ideally, you want M+1. But for this missing CR function, if you know that you have a no-way vanishing closed section of the canonical bundle, then you have local embeddability. So these theorems are quite, well, they're quite important, but maybe underestimated. And then there is another result that is due to Hill, Lewandowski, and Nurowski, which is, well, they call it a lemma, but I think it's quite important. Instead of asking for embeddability, you can ask whether there exists a local CR function in dimension 3. And the answer is yes, if you can find a complex valued 1 form that is in the annihilator of H01, such that omega wedge d omega is equal to 0. Okay, so I've reformulated all these theorems in terms of these BGG operators. So I will not go into details because it's quite technical. But the first one was actually concerned with this Hill-Lewandowski-Nurowski lemma regarding CR functions. So I showed, so let me go back to this equation. So I showed that this equation on the complex valued 1 form was equivalent to an equation on a 1 form, lambda beta, that satisfies an equation that I call the Webster-Weyl equation. So if you're familiar with the Einstein-Weyl equations, this will look very similar. So this is a CR invariant differential equation, nonlinear. And if you find a solution lambda beta to this equation, then you can find a CR function. And the other result that I've related to CR embeddability and the work by Jacobowicz is the following. So I proved that a CR manifold is realizable as a hypersurface in C2 if and only if there exists nowhere vanishing densities, sigma and tau, of weight 1, 0, that solves simultaneously these two equations. So here, this equation would look familiar from the operator I introduced earlier, except that there is this little xi on the top, and this is simply a gauged version of the Webster connection. And this is still CR invariant. Okay, so this is a gauging of my Webster connection. And similarly here. So in fact, these equations without the gauging were discussed in work by Curry and Ebenfeld in the context of obstruction flat CR manifolds in dimension 3. So actually, this is quite technical work. It's, their paper was published in Annals of Mathematics, I think. So there is some. I mean, so some people in CR analysis might just feel that these results, or even the results by Jakubowicz, might not be so useful for embeddability, but actually they found some use in one form or another in recent work. So these two results are new. Okay, so now let's move on to Fefferman's construction. So it's so I'm moving into the realm of conformal geometry. So as I said, Fefferman constructed a canonical Lorentzian conformal structure from a CR manifold. And I will review the construction, well, so from two different perspectives. So the first one, due to Chap and Gover, is from the perspective of parabolic Cartan geometry. So you have the flat model that I gave earlier on. So you start with a Hermitian inner product of Lorentzian signature on C2m+1, sorry, on Cm+2. And you have this cone of complex null lines. And you take the complex projectivization and you get, maybe I should erase this, and you get the odd dimensional sphere equipped with a CR structure. But I can also view this complex space as a real space, so now of dimension 2m+2, and it's equipped with a symmetric bilinear form of signature 2m+2, 2. So instead of thinking of this cone as a cone of complex null lines, I think of it as a cone of real null lines with respect to this symmetric bilinear form. And if I take the projectivization of this line, so the space of all these real lines, then I recover the flat model for Lorentzian geometry in dimension 2m+2. And it's not too difficult to see that this 2m+2 conformal Lorentzian geometry is fibered over this 2m+1 CR sphere. The fibers being precisely the well, circles. You know, the circles come about from the phase. So that distinguishes the real projectivization from the complex projectivization. Okay, so there is, of course, a curved version of this, and to describe it, I will use the approach by Lee. So, or actually, it's also the approach by Chap and Gover. So if I start from a CR manifold of dimension 2m+1, then I can, well, I defined a bundle, a circle bundle over it, which will correspond to my, well, which will correspond to this space, essentially, the curved version of this space. So this is one of these density bundles with the zero section removed, quotiented by the natural positive real number action. So how does it work? So I'm starting from my CR manifold and I want to construct a conformal manifold. So if I choose a contact form with associated Levy form H, so this is theta and then H, I have for free a Webster connection associated to this contact form. I have an induced connection on this manifold because it's an associated bundle. And I also have a piece of the curvature of this Webster connection, which is called the Webster-Schouten scalar, which I call rho. I take all these ingredients and I can rearrange them in the following form. So I pull back my theta, I pull back my H, and I pull back this induced connection, and I add to it a multiple of the contact form by means of this Webster-Schouten scalar. And this gives rise to a metric, which I call the Fefferman metric, which is of Lorentzian signature. Now, if I change contact forms, I get a change of conformal structure. So there are plenty of changes of these quantities, but the end result is that at the end of the day, the Fefferman metric of the new contact form is conformally related to the Fefferman metric I started from. So we have a conformal structure from a CR structure. In addition, we have a conformal killing field, which I call K, or K tilde, which generates these, the fibers, the circle fibers of this manifold. And I will call the triple M tilde, C tilde, K tilde, the Fefferman space. Okay, so once I've chosen my contact form, here I can interpret the densities of weight 1, 0 that I mentioned earlier on as sections of this bundle here. So if I choose, okay, so I choose a contact form. I have a contact, I have a Fefferman metric. And if I choose in addition, if I make a choice of density of weight 1, 0 that is, which is compatible with this contact form, I get a trivialization of my bundle. And there is a canonical coordinate on the fibers that I call phi, that I can use to describe the sections of this bundle. I will be using this in a minute. Okay, so maybe I should go a bit faster. So you might be familiar with a lot of conformal geometry. So actually, it's easier to start from conformal geometry and then describe CR geometry. But in this case, I will tell you that conformal geometry is like CR geometry. So instead of considering a conformal class of contact forms together with a complex bundle complex structure, you consider a conformal class of metrics. And in complete analogy to the CR case, you can construct density bundles that are denoted in this fashion. So in this case, I'm considering the top form, the top power of the exterior algebra of the cotangent bundle. And one can show that there is a correspondence between nowhere vanishing or positive, but nowhere vanishing, let's say nowhere vanishing sections of this line bundle. So nowhere vanishing density bundles of weight 1 and metrics in the conformal class. Okay. So, okay, so this is the, so once I've chosen a metric, I have a Levi-Civita connection and I can consider the curvature of this Levi-Civita connection, and it splits into a conformally invariant part, the Weyl tensor, and then the rest, which is described by the Trautman tensor. So then there is the problem of considering specific metrics in the conformal class that satisfy some properties. So one of them is, of course, if we're interested in Einstein metrics, we might consider a differential equation on the density that corresponds to the actual metric here. So the basic idea is you start with the conformal manifold and you try to find a solution to this differential equation here, which is conformally invariant, which is on the density of weight 1. If you find such a density, then you get an Einstein metric for free. So this was a result by Lebrun in 1981. And Rodgover, so typically, so Lebrun had in mind nowhere vanishing solutions. But Rodgover weakened the assumption that it is nowhere vanishing and allows for the density to have a non-empty zero set. And he calls a solution to this equation an almost Einstein scale. So it means that of the zero set of the solution, you get an Einstein metric, which is regular, which is smooth, but only of the zero sets. The metric is not defined on the zero sets. So you can, in the context of general relativity, you can think of this zero set as conformal infinity. Okay, so how do we produce such almost Einstein scales in the context of the Fefferman construction? So this is the original setting. So we have the CR manifold here, the conformal manifold here. And what I can do is I can consider a solution to the CR Einstein equation that I gave earlier on. So a solution to these equations. So it's this time sigma is a density on the CR manifold, and it has weight 1, 0. Then I can construct, well, this sigma gives rise to a Fefferman metric via the contact form, and also a particular trivialization of the Fefferman bundle in this way. So this would be the zero section, if you want. And from it, I can take a particular conformal factor, which is given in this form, sec squared of phi times this Fefferman metric. And it turns out that this metric here, well, first of all, because it's 1 over cos squared phi, then it's not defined for values of phi being plus and minus pi over 2. So this metric of these two sections here is Einstein. So this can be shown. So if it's Einstein, I can describe it in terms of this almost Einstein scale theta tilde. And the zero set of this sigma tilde precisely includes these hypersurfaces that are sections of the Fefferman bundle. Okay, so this is a nice result that was due to Felipe Leitner and Chap and Gover. But actually, Jurek, back in the 1980s, that was one of its earliest results. He was interested, in fact, he was always fascinated by the Fefferman construction. But in 1988, he showed that there are no almost Einstein scales for non-conformally flat Fefferman 4 spaces. So in dimension 4, everything is a little bit too boring with Fefferman metrics or Fefferman conformal structures, in the sense that they do not contain any Einstein metrics of these zero sections unless the manifold is conformally flat. So Jurek did not use the terminology almost Einstein scales, but this is what his result was about. Okay, so if this doesn't work so well for the Fefferman space, maybe we can do something about it. So one strategy that I had was to perturb the Fefferman conformal structure. So you start with the Fefferman space, with this conformal structure constructed from the CR manifolds. And then you take any one form, xi tilde, on the total space of this bundle, which is annihilated by the conformal killing fields generating the fibers. So it's a semi-basic one form. And if I take any Fefferman metric in the conformal class, Fefferman conformal class, and adjoin to it this one form in the following way. So this is the contact form of the Fefferman metric, and I take the symmetric tensor product with the xi tilde. Adjoining it to it, the Fefferman metric gives another metric, which I call the Fefferman metric. And of course, if you change the contact form, you get a conformal class. So you get a new conformal class that I denote C tilde, xi tilde. Now, okay, so this is a little bit technical, but here I will summarize this very quickly. So maybe I will hide it. So xi tilde is a basic, semi-basic one form on a circle bundle. This means that I can actually take the Fourier expansion of its components. And so I end up with plenty of data, which are precisely the coefficients of the Fourier expansions. And the coefficients depend only on the CR manifolds, since I'm taking the Fourier expansion along the fibers. So there is a technicality here that involves interpreting the coefficients as densities. I will not go too much into it, but this is in fact quite important. So the idea is that eventually from this semi-basic one form, I end up with what I call CR data. So the CR data is a whole bunch of densities living on the CR manifold. So I can recover the semi-basic one form from this CR data. Now think of them as being the coefficients of the Fourier expansions. So then I had this important result that I called theorem 1. So the characterization, and which has to do with our non-shearing congruences of null geodesics that you find in dimension 4 relativity. And I assume that they are twisting. So I start with the Lorentzian conformal four-manifold. So there is no metric here, only conformal structure. And I suppose that there is a vector field that is tangent to a twisting non-shearing congruence of null geodesics. So you should all be familiar with this, I guess. This is almost standard in general relativity. And then I impose these two conditions on the conformal curvature. So the first one is on the Weyl tensor, and the second one on the Bach tensor, which is the obstruction to finding an Einstein metric. So these are degenerate in some sense along the congruences. So the first one tells me that actually the Weyl tensor is of Petrov type 2. It's algebraically special, or more degenerate. Then locally, my Lorentzian conformal four-manifold turns out to be conformally isometric to a perturbed Fefferman space with CR data specified by a finite number of Fourier coefficients. So this is quite remarkable. So yes, as you know, these twisting non-shearing congruences of null geodesics are very important in mathematical relativity. So besides this theorem that is purely in the conformal setting, we may ask the question, what happens when we have an Einstein metric? So instead of considering Einstein metrics, I will consider pure radiation metrics. So essentially, well, so you should know that pure radiation metric is one for which the Ricci tensor has this form. So I allow for a cosmological constant and a pure radiation field here. So K is the generator of the congruence of null geodesics. I can turn actually solutions. Well, I can turn the existence of pure radiation metrics in this setting into a conformally invariant differential equation in terms of one of these densities. Yeah. So let's skip this technicality, but I'm interested in pure radiation metrics. So if I know that my Lorentzian conformal four-manifolds equipped with this twisting non-shearing congruence of null geodesics admits at least locally a pure radiation metric, then my manifold is conformally isometric to a perturbed Fefferman space with this prescribed CR data. So in fact, well, so there is a little bit more to it. No, I have my CR data as before, but this CR data is constrained in some way. So I'm giving you this equation in a CR invariant way. So they look a bit strange, but actually these equations are in the work of Tafel, Lewandowski, Nurowski, back of 1990, and later Hill, Lewandowski, Nurowski. So these are equations describing CR embeddability. So if I focus on this equation here and that one here, so these two here, I can massage them, I can make some substitution. And notably for this equation 3 here, I can turn this equation 3 into this equation here. So I end up with this equation and that equation. And as I showed before, this implies that the CR manifold is embeddable. So this is precisely what Lewandowski, Nurowski, Tafel, and Hill found some years back. So as a corollary, a Lorentzian conformal four-manifold endowed with the twisting non-shearing congruence of null geodesics and admitting an almost pure radiation scale is locally fibered over an embeddable CR three-manifold. But then maybe more to the point, we can describe these, well, any pure radiation metric in the context of twisting non-shearing congruences of null geodesics as a perturbed Fefferman space. And this, so the pure radiation metrics are not defined on hypersurfaces of this in space-time, which you think of as conformal infinities, and you interpret them as cross-sections of the Fefferman bundle. Yeah, I think this is all I wanted to say. Yeah, I'm running a little bit late, and okay, thank you for your attention.
Thank you. So maybe some short questions. Maybe in the room, there are some people that, oh, that's a good thing.
No, I haven't any particular question, but I want to see Arman, you know, so I switch on the camera, you know.
Okay. Good to see you.
Yeah, see you. So you are still in Łódź, yes?
Yeah.
Okay, so maybe if there are no questions, I will stop recording, and I don't know. So thank you.